context, the NTRU-based scheme is something that's out there for since the 90s, and actually started to form some context for financial crypto for some ANSI standards and whatnot. And then the variation of that, they actually didn't know at the time. They didn't have semantic security and all these other kind of nice properties associated with that. I don't know if you're going to get into that.
Yes, I will briefly discuss that. So maybe I'll get to the NTRU scheme, the original scheme in a sense, and we'll explain it a little bit.
And also a little bit more context is the NTRU-LWE scheme is the big thing that I've been working on for the past 4 years for DARPA and what I'm getting ready to show next week. And the NTRU-LWE scheme is a variant of that, is basically what we're focusing on in our open source library that we're building here, which is a really good thing to kind of dig into and get some general familiarity to it as opposed to just going right into the research literature.
Yes, our first pre-implementation will be based on the NTRU-LWE scheme.
Right.
So that's just so it's actually something that we're working on now.
Yeah, it's very relevant, especially to this group.
Okay, let's just make sure.
And it's also, for those of you guys in San Diego, the NTRU-LWE scheme, that's what we use for the VoIP application that we've been talking about.
So we're going to try to get it handle of the page down doesn't work, and let's just check up there. Sure. We'll try to get to the, because in the screen mode, I think it's kind of, let's get it back to the normal mode. Okay, just working. Oh, those two. Okay. Yeah. There. So before we discuss the scheme itself, let's introduce the parameters and what kind of polynomials we're dealing with in this case. So I'm going to look at the case of polynomial rings where the cyclotomic polynomials are basically correspond to the case of 2 to the power of 2 of n. And we had a discussion in lecture 2, so this is the simplest case. In other words, in this case, the cyclotomic order of the polynomial, and it's the polynomial that's used to define the polynomial ring by that polynomial. In this particular case, that m is equal to n, and that's a special case and the simplest case to consider. So in our case, the polynomial, the cyclotomic polynomial that we will virtually divide every expression by will of the form taken to the power of n plus 1.
And there's a lot of really good reasons, both mathematical reasons and implementation reasons, why we want to focus on that particular set of rings, where this is basically the power of 2. You that have experience in signal processing, anytime you got to do with FFTs that have power 2 indices, things become much simpler, and you basically can start pulling on a lot of the existing mathematics and software libraries that are out there. And so a lot of existing literature out there for doing that. And a lot of the simplest bootstrapping implementations for home encryption rely on power 2 rings also, where things become almost an order of magnitude simpler to implement by making that assumption.
And this case is also well studied from a theoretical perspective. So the security analysis improves abundant for this particular case, in contrast to the case of arbitrary exponent. So it's simplest, and it's the most well studied from the theoretical point of view as well. So important parameter in this scheme and in any Lattice crypto scheme is the so-called ciphertext modulus Q. So actually that's the restriction that we have for each coefficient of the polynomial. It's going from 0 to Q minus 1. And generally speaking, that ciphertext modulus will be a prime number, or in the case of a double CRT representation, which we'll discuss in future lectures, it will be a product of prime factors. But for simplicity, in this particular case, we're just going to look at the scenario when Q, the ciphertext modulus Q, is a prime number. I've already mentioned that for the case when we're dealing with the cyclotomic polynomials with power of 2, a ring dimension is defined, and the ring dimension itself is a power of 2, and value of the ring dimension itself is simply the order of the cyclotomic polynomial divided by 2. Again, this is true only for this special case. There are important characteristics that we have in any lattice crypto scheme, directly or indirectly, the parameters present, is the plaintext modulus, and that's the modulus that defines the how the plaintext polynomial is actually generated, or how the plaintext is transformed to a polynomial. And in this case, we're going to look again at the simplest case when the plaintext modulus p is equal to 2, which means that when we represent the plaintext as a polynomial, the coefficients are going to be either 0 or 1 of the polynomial. So that, again, this is the simplest case, but the one that can be can be implemented there. As we discussed at the end of lecture 2, a lot of so-called small polynomials will be generated using discrete Gaussian distribution. And for coefficient, and we're going to use it to generate each coefficient of the polynomial, and there is a bound introduced, the maximum value that a coefficient of the polynomial can have, and that bound, in other words, this is what we're what is written here mathematically. L infinity norm is smaller than or equal to b, so each coefficient will not exceed that upper bound b, simply speaking. So that's why we're considering the case of bounded Gaussian distribution. So this gives us the context of where this crypto scheme is applied. The text modules, the plaintext modules, and the dimension, which are the three critical parameters, and of course, discrete Gaussian distribution, is something that makes it all work. Right. Now let's go to the next slide. So let's look at the case of key generation. Key generation will be the same both for the conventional NTRU scheme that we're going to discuss and NTRU-LWE scheme. Difference will be in the way the actual encryption and decryption is done. So actually, we generate two polynomials, and again, those polynomials are in your mind, we had a discussion in lecture 2. Polynomial and ideal lattice, there are two equivalent concepts. So you can think of it as an ideal lattice, in other words, vector, or you can think of it as a polynomial. So those two are equivalent. So conceptually, it's easier for us to use the term polynomial. From the implementation perspective, for example, the term vector is probably easier.
Yeah, these things, although this is actually maybe the divide in the crypto community now, where you can tell the active cryptographer whether they're a theoretician, they call everything polynomial, or me, you're a knuckle dragging implementer, and you call everything by a vector or an array or something like that.
That's very important. So we introduce two short polynomials. So asterisk and G. The word short in this case refers to the fact that the discrete Gaussian distribution that is used to generate the coefficient has an upper bound of b for each coefficient. So none of the coefficients in those polynomials exceed that upper bound b. Relatively small number, compared to the ciphertext modulus Q. Both are generated using this big Gaussian distribution, centered at 0, and of course that bound b is related to the standard deviation. But we'll discuss that part a little bit later. So for those two polynomials, them is going to be used to generate the private key, which in this case also represents a polynomial. So the key polynomial is generated as 2 multiplied by this polynomial interest plus 1. Why we introduce is in other words, coefficient 2, which points to the plaintext modulus 2, and value 1 is to guarantee that the value of the private key applying the modular 2 operation will be congruent to 1. It's going to be one of the requirements to guarantee that our encryption scheme is correct. And actually, the decryption itself works. Also, another very important requirement that we will have for the key polynomial f is its inverse, multiplicative inverse q does exist. And the reason why this requirement is introduced is because the pi is defined using that inverse of the private key. So this is private key. The private key is accessible only to the public. For example, in this case, we'll be able to decrypt the data. The public key can be used by anyone to encrypt the data. In the conventional discrete logarithm scenarios, such as gamma encryption or decryption, so the same general idea is applied here, but we use key is generated as p divided by f. So you can remember the polynomial we generated using the Gaussian distribution, and we divided by the polynomial f. And the fact again is introduced to guarantee the decryption when to operation is applied.
And so I want to comment on the terminology a little bit, at least a little bit of intuition. So you see here that this private key that is, we'll say that, and this other kind of G type operation where it's basically like kind of about it as kind of like some random noise or something like that. And so if you think about the public key, it's basically being an operation is basically multiplying a ciphertext times its f. And though Yuri uses the terminology of division, it's actually, division is kind of funny in here. It's actually more like a multiplication by inverse, which is exactly what it is. In arithmetic, multiplication by inverse is actually division. And
it's still called division, but again, it can be confusing. Yeah.
I get a little pedantic about things like this. Sometimes I just call it multiplication by inverse. And so the encryption operation is intuitively at a high level being a plain text by a secret key, by a key, this public key, and by decryption is then multiplication of that by this f, times f inverse times f is equal to e. And secondly, have then this operation where it kind of strips away that extra little bit of noise, and that's the decryption operation. So intuitively, at a real high level, that's how a lot of these crypto systems tend to sort of look like. But the details of the math varies quite a bit from scheme to scheme. But that's kind of the overall how these things are generally built.
Yeah, and the general, and so far what we're looking here, this is the main logic behind NTRU. So any NTRU-based scheme has the definition of the public key. The logic is that if you're given a polynomial G and given polynomial H, it's mathematically, it's hard or virtually practically impossible to find the value of the polynomial f, which is the private key. So that's the so-called. I'll use the simplified term NTRU problem. And generally speaking, H will look uniform. So one of the problems that's formulated in NTRU context is to differentiate, to distinguish between H being truly randomly uniform and generated using this particular expression. So in mathematically hard problem, originally this problem was used for the NTRU scheme, which I believe was proposed first in 1998. That scheme was based on the polynomials, not cyclotomic polynomials, but the polynomials where I'll still use the word divide by xn minus 1, but generally speaking, the same logic applies in this case as well. So this is the conventional NTRU scheme used for the case of ideal lattices. Instead of cyclic lattices, we deal with ideal lattices. So and the fact that it's very f gives of H and G is the basis of the complexity. So now we have the private key and the public key. Look at the next step. So the next step, we're actually going to look at the encryption decryption scheme. And So we'll consider the classical NTRU implementation just for the case when we have the operation of modular xn plus 1, the classical NTRU implementation. So the stage in this case is performed using the is performed over polynomial things, and very important that we only use modular Q operations here. So we only apply the operation for the ciphertext modulus. So first, multiply our public key by certain the polynomial R, which is in this case generated using discrete Gaussian distribution.
So it's basically multiply public key by a bunch of noise.
Yes, just simply speaking by some. As in the conventional NTRU scheme, it's a uniform, it's a basically random polynomial and with a uniform distribution. In the case of that we're looking at here, synchrotonic polynomials, this is generated using discrete Gaussian distribution. So multiply this pi by noise, and we add the plain text polynomial expression. And so note that in this case, the polynomial is has only binary coefficients, so zeros or ones.
P equals 2 in this case.
Yeah, in other words, equivalently, you can say that P equals 2. So those plain text modulus equals 2, those are interchangeable. And R, so like we mentioned, is a short polynomial. So this particular polynomial C is called in the Lattice crypto world ciphertext error. That term will be used a lot, and the analysis of correctness of crypto schemes, Lattice crypto schemes, will be based on basically will be formed by analyzing on this ciphertext error. So ciphertext is also called ciphertext error. Very, very interesting concept that you won't see in other public key cryptographies. So basically, the ciphertext is sent to the file that has a private key and that will need to be decrypted. Decryption is done in 2 steps. First, just like Kurt pointed out, multiply the ciphertext error, or sex equivalently, by the private key polynomial F. Actually, I have to make a correction. So P is the ciphertext and B is the ciphertext error. So I went too far. So I just want to make sure that we differentiate between those. So C is the ciphertext polynomial, B is the ciphertext error. I went 1 step ahead.
Yeah, I am.
So we have the ciphertext. We multiply the ciphertext polynomial by the private key polynomial F. And this is performed with modular Q. So this is ciphertext error. And logic behind our correctness analysis, which we'll do in the next slide, is to make sure that this polynomial B, that none of the coefficients in the polynomial B will around Q. So the goal is to make sure that none of the coefficients will ever exceed Q, because they will make the decryption incorrect at the next step. So with this ciphertext error B, and then we apply another modular operation. And the modular operation is done using the plain text modulus 2, and this gives our result back. Let's look a little bit at the analysis, why this works and what happens on the back, on the back end. So let's first look at the ciphertext error at that expression. So we have the so it's defined as the product of ciphertext and the private key polynomial. Then the ciphertext polynomial can be written as HR plus M based on its definition. That's what was done by the encryptor. then we can use the definition of the public key H. So that substitute our definition of the public key in this expression. As you know from the basic modular arithmetic math, that multiply a certain polynomial by its inverse, or if you multiply a number by its inverse, you will get 1 as the result. Use that fact, this expression gets simplified to 2GR. So we 2 multiplied by the product of polynomials G and R. And as the second term, we have F multiplied by the plain text polynomial M. And is if text error polynomial D does not wrap around Q, and for practical reasons, in this case is set to Q divided by 4, and we'll discuss that later because that's a special topic. By practical reasons, this guarantees that this expression that we here never exceeds Q, and actually Q divided by 4, for any of the coefficients in the polynomials. For any coefficients in the polynomials.
So effectively what we're doing, and so this, I think, maybe we, rather than do a bunch of math every now and then, we should maybe give a little bit of intuition.
Sure.
So effectively what we're doing is that we're ciphertext, we're encrypting it by adding a bunch of noise and multiplying it by this, plain text, adding a bunch of, adding a bunch of noise to the key, and then adding it to the plain text to actually effectively get the ciphertext. And then the decryption step is basically multiplication by the secret key again. And we have this funny step of stray bunch of the noise that are out, and this B vector that's out there, like doing a bunch of modules operations. And effectively the way we choose the keys and the noise the way we do is that actually know, based on proof, to have this decryption operation, which is effectively kind of like a modulus type, a generalized modules operation. And so dive down in the details a little bit. We probably will as we go through different schemes. But the high intuition is that you choose this noise and you choose these in such a way that once you get this ciphertext noise that's left off after you do the decryption step, that you can basically run this fancy modules operation to have everything work out. The proof that's associated with is also proof that the noise is not too big, that you can still have modules operation also. So
that's what's related here in this inequality, and that's the basis for the so-called correctness inequality constraint. Of course, if this is true, then after applying mod 2 operations to this expression, we have anything multiplied by 2 will be congruent to 0, so that term can be eliminated. We have multiplied by M mod 2 as the result. And we remember from the definition of the polynomial f that it's congruent to 1 mod 2. That was a requirement when we used the definition 2 multiplied by f asterisk plus 1. This is the reason why we did it exactly this way, so that this expression would be, this f mod 2 would be congruent to 1, which means that this is congruent to m mod 2, and m is our plain text polynomial, so we just recovered our plain text. So that we just performed. So the next we're going to look at the slightly modified scheme, and that scheme was modified to improve security, to introduce the Ring-LWE problem. The security of, I do want to make a note that the NTRU scheme it's indirectly related to some lattice encryption problems. It requires very careful selection of parameters to be really secure. There are a lot of known lattice-based attacks against the NTRU scheme. If you would use this scheme, we would have to have a very complex algorithm of choosing the right parameter selection, so we don't run into any of those attacks that have already been implemented. So that's why we're going to introduce an extra security by tying it to the Ring-LWE problem.
So I want to give a couple anecdotes. So this you know, the 90s was a very interesting time for many reasons. Bill Clinton was in office, MTV was popular, and they still played music, and people started looking at Lattice crypto. The internet was becoming popular also. And NTRU was developed by a bunch of cryptographers from Brown University over in Rhode Island. And NTRU, so when you see a bunch of these crypto schemes, like you see BGB, it usually means someone's names, like BD is Brett Goreski, Gentry, Bakanapa, and other things like this. NTRU is actually a little bit different in that supposedly doesn't really mean anything, but what I've been told is that it stands for a number of theorists are us. So it's kind of funny in that way. The guy from NTRU, startup also called NTRU, and a bunch of noise back in the 90s about getting it basically certified and standardized with respect to ANSI and IEEE for a couple applications. Actually able to get a couple standards out and usable out in the real world. Anyone actually uses it anymore, I really don't know. But in some sense, it's been helpful for us as we go through our work developing crypto systems that we can get the early NTRU work from the early 90s and say, hey, you know, it's been accepted by ANSI, and it's been accepted by IEEE, and that's why, you know, this stuff isn't totally, you know, off the wall, just academic gobbledygook. It's people actually use it. NTRU had problems because it had the property where it basically lacked something called semantic security, and you're going to get at that in a little bit. But it had some really nice properties associated with it in practice, and that had other public key crypto systems like RSA and the various elliptic curve versions and things like that. Asyncly, this actually provides much better performance in terms of encryption, decryption than RSA and a lot of the other public key crypto systems. Which is a really nice thing if you're going to be using it for manipulating a real lot of data, or you want to do things really securely. And we'll talk about parameterizations as we go through for different things later. And there's been significant growth based on this for a lot of the more practical lattice-based crypto systems that have been out there. And we'll talk about the ecosystem of that there also.
And so it's post-quantum as well, although it has, I mean, basically the levels of security, especially semantic security, are much lower than for Ring-LWE, but it's still much more secure than, say, a discrete logarithm problem in the quantum context.
Yeah.
So also another.
And so there's also other things about that, but NTRU has subsequently been bought by another company, and I believe it's currently being used mostly for like embedded system type applications, like vehicle-to-vehicle communication and stuff like that, or things that can run on embedded devices like FPGA type things pretty efficiently. And this is actually kind of cool. And I was actually trying to push Osho a little bit into looking to try to break their crypto system to see if we can actually do some hard stuff and put them out of business. But you know, that remains to be seen also. But it's actually the nature of research. You want to create new business, and you want to destroy businesses at the same time. So, anyway, get into it.
Okay. So,
I'm sorry, question?
Reservation, it's P mod Q, after that it's 2R, and in the next line there is no question.
Because it's 2, anything multiplied by, so if you say 2 mod 2, that's 0. And basically, if you multiply 0 by anything, that's...
Just one second. I'm sorry if there's all that well. Oh, it looks like no one's really making chats. Anyway, okay, good.
Okay.
The San Diego has been a little quiet.
So let me make sure I get back to this one. Yeah, I'm back now. So now we're ready to talk about this scheme that we're actually implementing now in the CryptoLab.
Yeah.
So the difference between this scheme and NTRU scheme is that we add an extra term with a noise, with an error noise. And what we're doing here is actually, if you look at the first two terms, H multiply S plus 2E, you'll probably remember from the previous lecture formulation of the Ring-LWE problem. And the formulation was the following, that if given a certain random, in this case polynomial, and we perform this, actually set of operations using polynomial E with discrete Gaussian distribution. The answer that we get from this expression looks uniform. So the end result of this operation looks totally uniform. So one of the problems is to distinguish between the fact that it was generated using a scheme like this, or whether it was randomly generated using some pseudo-random generator. So generally speaking, we're embedding the LWE problem by adding this term to E in this case. So the security of this particular scheme is based on the security of two problems. One is the NTRU problem, which in a sense guarantees that this polynomial H is uniform. And the second is the Ring-LWE problem that guarantees that this expression is uniform. The Ring-LWE problem is much stronger in the mathematical sense. So this is why we have a formulation like this from the security perspective. Everything else here is very similar, other than that we have an extra term, extra error noise, and this E is called the term in the Lattice crypto terminology. So everything else is very similar, and this E also generated as a short polynomial. And process is exactly the same conceptually speaking, with only difference that the ciphertext polynomial is different. The ciphertext polynomial also includes the noise term. But exactly the same. And the goal of adding this extra term is to enhance the security of the scheme. This was done for the sake of security.
Right. So I think it might be illustrative to describe at a high level, intuitive level, the attack that would work on the older version of the scheme, but what is the newer version?
Yeah.
Yeah.
And yes, and so all of the known attacks against the NTRU scheme are virtually kind of become useless after we introduce this this noise term. Yeah, I'm a little oversimplifying, but still that's generally true.
Right.
Okay, proof. The proof is very similar again to what we did for the NTRU scheme, with the only exception that in this case the ciphertext error contains one extra term multiplied by the private key polynomial f multiplied by the noise term. So everything else is exactly the same, and we understand why we had the number 2 here is that when we apply the mod 2, and actually mod in this case is mod 2 operation, this particular term is eliminated. It's cancelled. So after we apply the mod 2 operation to this expression, the first two terms are eliminated, and we only have f multiplied by m, just like in the case of NTRU. And of course, the key polynomial f was defined in such a way that it's congruent to 1 mod 2, and this is back to plain text polynomial.
You're longest here. So, a quick question. It's the polynomial this polynomial. Is there any difference in the generation for that polynomial? In other words, is there a different bound on the discrete Gaussian distribution? Because it would seem to me if you have noise, then you're going to violate that b less than q over 4 constraint if you add too much noise to the polynomial.
That's actually a very good question. So in this particular scheme, E is generated the same way. So E is generated using the same bound, B, and so there is no difference. And then a very good point is to make sure that we do not wrap around the value of Q in the ciphertext. There are a lot of studies talking about the choice of specific polynomials. For example, the polynomial S can be chosen as discrete Gaussian, or it could be even chosen as uniform. From the mathematical perspective, those two are equivalent. Then I think there are some. I've seen some literature discussing reducing the bounds in certain polynomials. So that is definitely an important especially when we look at the correctness inequality constraint analysis.
Right, and in fact, there was just a really, really recent result that I just came across actually last night of all things. Well, an academic cryptographer was basically able to show that for very, very specially chosen rings, there's actually very, very effective attacks against some of these systems. The rings are actually kind of rare, and most people will actually use them. But these do have a propensity of falling apart sometimes if you're not actually careful about some of these choices that we're talking about.
Yeah.
Right
So again, there is a trade-off, and we'll take a look at this further. On one side you have the security, on the other side you have the efficiency and more of the correctness. In this case, we want to make sure that that ciphertext error does not wrap around, and there is and always this. I mean, we're kind of trying to play with those two, and when we look at the next in the constraints, we'll see how that actually works out. Yeah.
What is the condition that when 2/4? What do we mean by that? What do we achieve by that?
Simply speaking, you can in your head you can replace it with B is less than Q. If the value of B or coefficient in the polynomial of the ciphertext error exceeds the value of Q, the result that you will get at the next step will be different. I mean, it depends. So it's no longer this step is correct only granted that the first step never wraps around Q. Because, example, an odd number can become even, and when by the mod 2 operation, this will no longer correct. Just simply speaking, that's what they have. Yes, less than Q, but divided by 4, that's first of all the implementation. I don't want to go into those specifics. It's generally speaking, it's less than Q, but when implemented, it's Q divided by 4, and it's not that detail is not that important right now, so we can discuss it later. This is more for an implementation sake. We're getting to the most interesting part. So the part that deals with parameter selection. And generally speaking, we have 6 independent parameters, but we deal with 7. So one of the parameters is derived. Okay, I'll use basically the case when we have 7. So I'll treat the derived parameter as one of the parameters. So 5 of those parameters are static. In other words, choose them based on you choose them for a specific scheme. That you take them from, for example, reference books. You take them from certain facts known about the discrete Gaussian distribution. And then 2 other parameters, and we'll discuss them in the next slide, the ring dimension and the ciphertext modules, where we actually perform optimization. So the 5 parameters are given, and then we'll perform the optimization for 2 other parameters. So in this, the plain text module is given. So we're dealing with binary plain text polynomial. The security parameter, which is also called the root-Hermit factor, and Kurt can probably talk more about that parameter. So that parameter is chosen on those lattice crypto problems. In this case, approximated shortest vector problem, and it results in a certain level of security. There is a lot of, there are a lot of mathematical studies dealing with this. Plus, there are a lot of experimental studies. So there's a theoretical side. There is experimental side based on a large volume of those works. Those magic numbers 1006 or 1007 were computed. And maybe
right. And so yeah, this is actually a preview of coming attractions. So there's a lot of things that are wrapped up into this, and actually a lot of actually even regular issues wrapped up into this also. I've been talking with Rugai and Osho about doing some cryptanalysis type work, and it's tied in a lot of this root-Hermit factor, both mathematically and experimentally, about how you design things that can crack these crypto systems. In fact, running things on the cluster are going to be set up here in the next couple of weeks here at NJIT based on some donated servers we're getting from a local cloud provider. But the root-Hermit factor is come to be a representative indicator of security. of these crypto systems.
Security level, in a sense.
Yeah. A lot of these crypto systems, you care about something that's called work factor, the amount of effort it requires to actually go and recover a key with brute force computation or some other smarter method you have. Work factor can be kind of hard to talk about how it's a factor of 10 trillion expansion or something like this. The existing crypto systems, people have come to key length, number of bits in a key as a representation. Of course, very apples to oranges when you start talking about key lengths of RSA versus key lengths of AES. And also because various problems are based on various hard computational problems. The Fermi factor is actually the probably the hardest problem for a lot of these lattice-based crypto systems, based on the closest vector problem, the shortest vector problem. And one thing that also why I like the root Fermi factor is that if you look at the export regulations for the State Department of Commerce in the States, ITAR and EAR, for those of you that haven't heard of them. A lot of these regulatory concerns are driven by whether you export crypto software is how big the key is. Bits are actually in the key. You have to actually fall into different kind of regulatory issues. I've always held that those kinds of key length determinations of security don't really work because it's actually very, very hard to the security of AES versus RSA. So it's kind of arbitrary. I've been pushing for having different issues drive the determinants of security, and I was even able to get a nice bit of a nice formal letter from the Department of Commerce on U.S. government letterhead that really said the last crypto system I built, that because Fermi factor was the prime determinant of security, that go forward and export it because it doesn't fall under regulations. So this is, I wasn't trying to say, I wasn't at all trying to pull a fast one of the U.S. government. I was, just trying to illustrate to them that these matter, and actually found someone on the inside who agrees with me. So actually kind of nice, and so that's why I'm trying to push our community of doing lattice crypto security in terms of something that actually has some real meaning, which is Fermi factor. Frankly, some of my academic colleagues agree with me because they might be trained to think about terms of bit length and stuff like that. But this group, we're a Fermi factor group, so that's the way we're going to be. So there's very few things I just tell people, that's the way things are going to be, but this is one of the few things.
So the next parameter that can be considered as static is the standard deviation. So discrete Gaussian distribution, we understand what standard deviation means. So generally speaking, we choose a value between 4 and 6. The following parameter, assurance measure, is alpha, was used in defining the bound for coefficients generated by the discrete Gaussian distribution. Is really a parameter that tells us that if we generate a coefficient using discrete Gaussian distribution, parameter alpha tells us what's the probability that the coefficient value will be outside the bound, outside the value of b. And generally speaking, for the case of alpha equal to 100, the probability that the value of the coefficient will be outside bound b is taken to the power of minus 100 plus 1. So in other words, it's 1 divided by approximately 2 taken to the power of 100. That's the probability that the coefficient that we choose will be outside the bounds. And in particular scheme that we're looking at now, if such a improbable event occurs, we can always resample coefficient so that we get a value inside that range. But for practical reasons, we're never going to go outside that bound. So that alpha is just the probability that and will go outside the bound. Those 4 independent or 5 in total parameters, the 5th one is derived, can be considered as static. We choose them based on criteria outside of the crypto problem or encryption or decryption. We choose them based on reference books, based on some of our knowledge of distributions, discrete Gaussian, or the actual shortest vector problem. So the next 2 are the parameters that we optimize. And 2 parameters are the ciphertext modulus Q and the remainder. dimension. We actually have two inequality constraints based on security and another based on correctness. We will need to apply, and virtually we're solving an optimization problem, trying to find the smallest values of the ring dimension and of the ciphertext module Qs that make scheme practical. So our goal, based on those two inequality constraints, to find the smallest values of Q and N, because they're obviously the parameters that will be important for our computations. So that's what we're trying to do from the kind of practical perspective. So security constraint is we'll use the same formula for any scheme that's based on the Ring-LWE problem, and this is actually so it's for several different schemes that I've seen for Ring-LWE, and it doesn't really change that much. The other correctness constraint depends on the specific procedure that we use to perform the to compute the ciphertext error, to compute the ciphertext itself. So that second one, correctness constraint, is something that we need to estimate just using some basic mathematical analysis before we implement the scheme or before we run the scheme. The focus of the next couple of slides is how to come up with expression for that second inequality that can be used for the optimization. As you remember, we generated the polynomials G, S, and E using discrete Gaussian distribution, where the upper bound of any coefficient in the polynomial was bounded by B. So it's safe to assume that the maximum absolute value that we can have for any coefficient of the polynomial will not exceed B. For the private key polynomial, since we introduced this as 2 multiplied by f asterisk plus 1, the bound can be larger, so and the larger can go up to 2b plus 1. Then consider the fact that the plain text polynomial is a binary, so we can have zeros or ones as the coefficient. The maximum value of the coefficient that we can have is 1. When we put all those things together, in other words, when we take the maximum absolute values, maximum upper bounds, and all the polynomial multiplication operations that we have here, we can derive the bound in terms of n and uppercase b. And the logic here is that we multiply two polynomials, in addition to considering the upper bounds for each, for the coefficients in each of the polynomials, you need to multiply by n, because the multiplication of polynomials will imply certain summation of n terms, generally speaking. If you think about the multiplication of two polynomials, you can immediately think of the fact that you will have up to n coefficients when you perform the multiplication. So that fact is reflected in the factor n. And basically, what this gives us, it gives us the constraint for the ciphertext modules itself. So b is less than 8 multiplied by n and b squared. And then that we have b1 q divided by 4. This traces to the correctness inequality q is larger than 32 n b squared. Again, remember that b is the parameter. We can always write down as alpha. So we derived our correctness constraint. In particular, constraint can be called pessimistic or conservative, because it take into account the central limit theorem in the fact that we're dealing with relatively large samples when we perform polynomial multiplications. So in other words, there is a way for us to come up with a smaller bound for Q, and we're going to do that next.
Yeah, so effectively, this is actually, might just jump in here a little bit. And what we're going to be seeing this a lot as we look at different crypto systems, the customization, tuning for these various crypto systems. Are we ever actually going to get anything that's going to be so clear cut about, what are the performance trade-offs associated with these things? This NTRU-LWE scheme that we're set up to be basically a very basic crypto system. We're not doing any kind of like proxy encryption. We're not doing any kind of homomorphic operations. We're not doing really any kind of funny stuff on there. So we get this kind of cleaner distillation of what the performance constraints are to get correctness. Be able to tamp it down a little bit more, but maybe not so much. And so if you go back to that previous slide, Yuri, let's see a lot of these kinds of constraints. And typically, as we, for example, look at optimizations of proxy encryption schemes, or homomorphic encryption schemes and these other kinds of things, there's actually multiple sets of equations. It's looking at just the correctness of, success of decryption. Other than might look at, various things like depth computation supported, and even other things about, you could probably even layer in a couple of equations in there if you wanted to about or runtime, as we want to look at these various optimizations. And a lot of what we're going to be doing, is going to be a non-trivial component of what we're doing, both and experimentally, is looking at how to optimize those constraints for the various performance, functionality, risk-time kinds of trade-offs. Go forward.
Yeah, of course, what we're looking here is it's just an decryption scheme. In the case of PRE or FHE, we'll have multiple stages and we'll have certain additional constraints introduced, or basically those bounds will increase based on the types of operations that we need to perform. Let's discuss that later.
Then how is this model introduced in the model?
And it's two.
Oh, yeah. This particular, right? Is that your question? Yeah, because
I think she's asking where did these ends come from?
These ends come. So when you multiply one polynomial by another polynomial, generally speaking, you have a summation of n terms when computing a coefficient in front of one. Basically, of one of the components of the vector or the polynomial. That's what when you compute one, and you'll actually see it in the next slide.
So basically, there's three equations at the top that basically got from the constraints up above to guarantee correctness for decryption, and there's effectively that happens, and it gets down to this bottom step where he basically combines a lot of those kinds of things into one pretty tight encapsulation of that representation.
The next example, just let's go there.
So that would probably be a good homework assignment for one of the last lecture of your 408 class or 608 class where you teach on crypto.
Yep, absolutely.
So yeah, this just has a heads up, right?
Yeah. So actually, you'll see. So as far as the end fact, you see an example here. So. So in case we devise an optimistic constraint, so in other words, a lower upper bound for Q, which means that we can use a smaller Q to perform secure computations. And I probably won't discuss this in detail. When you look at the slides, you can kind of go through the logic. But generally speaking, whenever you multiply two polynomials for each coefficient of the resultant polynomial, you will have a summation of up to n factors generally. And this is just an example. In this case, I chose one of the combinations. Of course, for each coefficient, you will have similar logic.
It's actually a fairly common trick that basically when you perform a polynomial multiplication, you basically keep the product of the first two terms, and everything else is kind of like can treat it as noise effectively. And that's really what Yuri's doing right here, is that he's keeping the terms, and they say all this dot.
Yeah, just to illustrate the idea. And you see that we have, the number of those terms is n. So basically, that's where we have, so each host has a bound, for example, b or 2b plus 1, whatever. So now you get n multiplied by, b, b squared, or n multiplied by b to b plus 1. And what that means, since we have a lot of independently generated so we have certain distribution, and from the population of that distribution, we generate a lot of variables. And this can be represented as a variable because we use it in the process to discrete Gaussian generation. This also makes it possible, the fact that we're doing a summation of, in a sense, independent cases of the distribution. This allows us to use the standard deviation of the sample and to reduce the bound that we have for this. And using the central limit theorem, we can reduce that n that we had to square root of n. So basically, we can divide it by square root of n because the standard deviation of the sample, for example, the average for the sample, is equal to the standard deviation of each component of the same distribution divided by the square root of the number of terms. That's what we're using in this case. So that trick allows us to reduce the constraint on n, and instead of having their function of n, we have a square root of n, which is a big improvement. So we can use statistics, just basic statistical analysis based on central limit theorem to come up with an optimistic bound. And technical reasons, this bound will definitely be more than enough. So all these operations, if we substitute all the numbers that we have here, we just two very simple inequalities. I mean, they're not, it's not a linear programming problem, but they're rather simple. And we can use those.
It's basically just two variables in there.
Yeah, two variables. I mean, the difference is a little bit like you have log and it's incidental a little bit, but still, it's a very easy one to solve. I'm using mathematical method.
Basically they don't have any kind of crossing in this first derivative.
Yeah, and this is kind of the summary of what, just performing very basic analysis of this.
Guys, to be pedantic in the last slide, which log are we doing? Are we doing log base 2? I was always taught log base.
Well, log base, so it's kind of, I'm now used to that in the crypto community, it's always log base 2, and I started using that. Yeah, I know it's, generally speaking, in the traditional mathematics, it's log base 10 when you simply write log, but it's log base 2, sorry, yeah, it's log base 2, of course.
Or if you're used to MATLAB, then it's always log base E.
Yeah, but in mathematics, when you don't specify the base, it generally is look for log base 10. When you use like ln, it's for the number E, and for in this case, it's log base 2. So everything here is basically.
So this parameter selection, these parameter sections, you don't actually count for the security factor.
So two constraints. So some of them are basically come from the security constraint, so the second inequality, and this comes from the first. This is why I wrote it this way.
Security constraint where you basically have a hard limit at delta equals 1.006.
Yes, and so this is like considered the static parameter in this case, which comes from. I'll use reference books. Yeah. So it's but still for practical reasons, it's definitely justified. So so you can you have those slides. You can quickly check this. It's very basic math. Generally speaking, I was trying to focus on the ranges of so what are the values of n that make sense to 10 to 11. What values of q are supported by the security constraint, and I looked at the correctness constraint, and after intersecting the two, the smallest numbers of n and q that will satisfy both the security and correctness constraint would be n equals 2 to the power of 10, so 10 bits, and q approximately, we'll have 21 bits, obviously. It's a prime number, but close to, it will have something close to 21 bits. So for this particular scheme to be secure, the most efficient based on the constraints that we used, of course, would be these two parameters. So, and then we have the problem with 7 parameters defined, and then we start computation.
So this is actually something that's really important. I want to kind of highlight these two things in particular, these optimizations. This ring dimension. So effectively with these, you're going to be dealing with vectors that are basically the 1,000 points in C's. to some extent actually fairly reasonable for a lot of the hardware that we currently have. I mean, Jan, you've been doing a lot of FPGA work in the signal processing world. You know, have you actually seen people doing 1,000 points FFTs before?
Yeah, it's common.
Really common, right? Right, and this is not out of the realm of crazy talk like, you know, n equals 16,000 sometimes is that, you know, things we have to deal with on other spaces. And then this Q, this is effectively the ciphertext modulus. And the thing here is the ciphertext modulus is on the order of 20 bits, which is reasonable. The modern processing systems, I got my Nexus 5, and that's got a 32-bit processor in there. And so doing, you know, manipulating 21-bit integers with 32-bit processors is actually quite reasonable. Even like the 64-bit processors like we have in modern laptops and whatnot. As you start to go down, you're dealing with like embedded systems and maybe like a 16-bit processor. You know, there's a little bit of other machinations you got to do, but it's not out of the realm of possibility. We start going real small, like 8-bit processors, you know. Good luck. Because effectively what you do when you want to do at a real low level, if you want to do, for example, use an 8-bit processor to do 21-bit manipulations, you have to, you know, schoolyard multiplication, you have to do a lot of carries and adds and stuff like that. You have to do a lot of that manually if you want to do this with an 8-bit processor. But just, for example, 32-bit processor or 64-bit processor is really quite, you know, natural in a lot of so this is another thing, this ring dimension and the ciphertext moduli, the cyber bits that require are things that we're going to have a lot of attention to as we start talking about the implementation of these kinds of things. And actually, it's one of the things I'm wrestling with to get, you know, kind of tamped down for next week also. I'll talk about that later. The San Diego guys will see some of that next week too. Sure.
That's actually this last slide. If you want to ask any questions, and I'll be.
Oh, great. Actually seeing some of the chat that's coming up from San Diego. So we'll start from there. So I think this is the last slide, as Yuri said. Are there any kind of questions? I know we're a little bit over an hour, but we started a little late also, but a little over our scheduled hour. Here in New Jersey, or anyone in San Diego?
We're in good shape out here. I don't want to speak for anyone else, though.
Okay, I had one question here in New Jersey. Mayor?
Yeah, can you please explain the previous slide that how n got reduced to root of n, the previous one?
This one?
No, I think it's the previous slide. So the reason why we got square root of n is, so we used to have the linear term for n, which corresponded to one multiplication of polynomials. Mm-hmm. When we perform the multiplication of two polynomials, the standard deviation of the sample involved in the summation for each coefficient of polynomial is equal to the standard deviation of each term divided by square root of n. That's by central limit theorem. So prior to this, each multiplication we had n multiplied, for example, by b squared, which, you know, and this n gets reduced because of the standard deviation by square root. So n divided by square root of n, square root of n, that's why we got that expression. By central limit theorem.
Yeah, Fiona.
Can you just explain why it's difficult to create the hardness of the problem?
So the hardness of the problem comes from this closest vector problem that we discussed last week. And what it is that if you think about the basis, right, is a pile of matrices, a set of vectors, right, linear independent vectors. And the computational problem is basically to find the linear summation of the vectors to find this as close as possible to the origin. And that gets into, you know, computational algorithm theory and stuff like that, but that problem is actually quite hard. And so the challenge of, and you're probably better able to explain what the connection is from the closest problem to this.
Yeah, I think this particular is the approximated, so polynomial approximated formulation of the shortest vector problem. So in this particular, I mean, the problem that's used here, but generally speaking, they're all they're related to the problem of lattice reduction. So, and in certain, and the problem of lattice reduction this is basically considered as a mathematically hard problem. And as you remember, in the first lecture, we discussed 7 different problems in Lattice crypto world. And it was shown that a Ring-LWE problem, actually the LWE problem, learning with errors, is equivalent, in the average case scenario, is equivalent to the worst case scenario for some of the Lattice crypto problems. And that's kind of how that security foundation came about from Lattice-based problems and certain problems such as learning with errors, which are defined in matrices, and that's on machine learning actually, and on the concept of reductions, and that's common in NP-completeness analysis in mathematics. You can show that one problem is equivalent to another, and at the end of the day, we were able to, not we, but the mathematical community was able to get a certain reduction to the, that's basically for the problem ideal lattices for the polynomial approximated case of the shortest vector problem, and that's what makes this work. Right. Simply speaking, well, I don't know if it's simple, but it's in reality it's much harder than what I described.
Yeah. Okay, from New Jersey or San Diego?
Not from us here in San Diego, I don't think.
Kurt, do you think, would you be able to send us the record I missed last week, and that's the one I was really interested in catching?
Yeah, I will. I had recorded them, and frankly, there was a compatibility issue with my laptop, and frankly, I just got, if you want easy, to actually go and do that conversion because in WebEx, it has this proprietary format. So I should have the software. I just got to find a computer that's compatible with the software to do that.
That's great. That's great. Thanks.
Yeah. And, so as far as next week, I think I'll be down in DARPA, and some of the space guys will be there also. San Diego people will be there also. I think we're going to defer any kind of regular seminar next week and week after. But of course, if you guys want to meet and talk and stuff like that, who am I to say no to that? And so I was thinking about what paper to read and whatnot. I know we traded some email a little bit. Maybe actually the Node's multi-key FHE paper. I think that might be a good way to ease into some of the research community.
For this scheme, for sure.
Because it builds directly on what we were talking about right here, and also gets in some of the standard conventions that are used in the community. And that's actually something that might use for actually an upcoming BAA that hasn't been announced yet.
And it's one of the simpler papers.
Yeah, it is also one of the simpler papers too. And good guys, who we talk to pretty regularly. So we'll talk about that next week also, and we'll trade some email about that. So,
yes, thank you.
All right, we'll see you guys next week.
Yep, thank you, Kurt. See you next week.
Bye, thank you.
Thank you, Ray.